All right, good afternoon, class. This will be our first video. This course begins with a look at differential equations. Essentially, a differential equation is simply an equation that contains derivatives or differentials. And if the equation contains only first derivatives, then it's called a first order differential equation. And in this first unit of the course, we're going to look at two different methods of solution for these first order differential equations. And the method we're going to begin with is called separation of variables. And it works like this. Originally, you'll have an equation of this form. So you'll have a differential dx and a differential dy. And then you'll also have m and n, which can represent constants, functions of either x or y, or functions of both x and y. And what you want to do is take that equation and perform some manipulation on it so that it is of this form, where a is a function only of x and does not contain y, and b is a function only of y and does not contain x. Okay, so in other words, stuck to the differential dx, there will not be y's. And stuck to the differential dy, there will not be x's. Okay, and then once you have that correct form, all you have to do is integrate. So here, integrate a with respect to x, and here integrate b with respect to y. And that will be the solution. Okay, so I'm going to show you also this page of formulas. I've put a copy for you in Blackboard for your reference, but essentially these are all inside the front and back covers of your textbook. So you've got your Washington textbook, and if you just take a look inside those covers, you'll find the derivative rules, some integral formulas, as well as some basic trigonometric identities. And really this part here, right in the middle, which you'll find at the back of your textbook inside the cover, this is what we'll need at the beginning of this course. Okay, so I'm going to go through some examples with you now. So I'm taking these examples right from your textbook. So this will be from exercises 31.2, which begin on page 954. So here we go. Here's question 4. Y squared dy plus x cubed dx is equal to 0. Now, the interesting thing is we already have proper separation of variables here. Beside the differential dy, we have a function of y, and immediately stuck to the differential dx, we have a function of x. So we can begin by integrating each of these terms. So when you integrate y squared with respect to y, you simply use the most basic integral rule. So all we do is we add 1 to the exponent, so it becomes a 3, and in front, of course, will be 1 over 3. So the integral of y squared is 1/3 y cubed. And x cubed is integrated with respect to x in the same way. So the new exponent will be 4, and here we will have 1 over 4. And now all we have to do is make sure that we correctly use a constant of integration. Okay, so I've labeled that C. When you go and check your answers in the back of the textbook, you should be aware that they would at this point in time clear out these fractions by multiplying all terms by 12. So this would then be 4y cubed plus 3x to the power of 4 is, and here we would have 12 times the constant. But what we'll do is call this first one C1. So here would be 12 times C1, which we'll just name constant C overall. So I'm going to put here in brackets that C is just 12 times the original constant. It wouldn't make sense to leave this 12 times C1 here, where C1 is some arbitrary constant. So in the final expression, the constant will always be labeled C. Okay, but the key is integrate, include a constant, and then eliminate the fractions. Okay, let's try the next one. This is number 8 from the same exercise. Now, this differential dx is certainly no good here in the denominator. So we're going to begin by changing division by dx into multiplication by dx. So that's going to look like this. Okay, so that's our first step. We get the differential out of the denominator. And now, stuck to this differential dx cannot be y. So this means that what I should be doing is now dividing by y. And that would look like this. So we can have 2 times dy over y is x plus 1 over x dx. Okay, now this is something that we're going to be able to integrate. You might not remember it right now, but it is found here. Okay, except this is du over u, and its integral is ln u. We have dy over y, so its integral will be ln y. So certainly we can integrate this side. When it comes to integrating this side, we should split this into 2 terms. So the 2 terms are x over x, which is 1. So I'll do it in little steps. X over x plus 1 over x. Okay, so that's just splitting it. And then, of course, it becomes 1 plus 1 over x, like that. And furthermore, we can apply the dx to both terms. So this just becomes 1 dx plus dx over x. Okay, and now we're going to integrate all 3 of the terms. So again, the integral of dy over y is ln y. So we end up with 2 ln y here. The integral of 1 with respect to x is just x. So since the derivative of x is 1, the integral of 1 is x. And here, this again is logarithmic form. So this becomes the ln of x, just like that. Okay? And then there would be, of course, a constant somewhere. So I think I'll just put it here. And I want to show you that the textbook also would combine the logarithms in this problem. So using properties of logarithms, this 2 coefficient can become the exponent right here on y. And I might as well bring this logarithm to the left side as well. So it'll be subtracted. And now we can combine the two logarithms. When we have subtraction here, it corresponds to division in the argument, like that. Okay, and it is finally solved. Now again, I did tell you in the little introductory video that at first you're not going to remember how to integrate very well. So it will take some work on your part to remember these things. Certainly this is the most basic integral rule we used here. And in this question, really we just had to know how to integrate dy over y and dx over x, so those are logarithmic form, and also the integral of 1 with respect to x would be equal to x. And another way of looking at that is the derivative of x is 1. Okay, let's continue. I'd like to do a few more in this first video with you. So here's the next one that I've selected. So we're not necessarily going in order here. This is actually problem 14. So when it comes to separating the variables, pay attention to where the differentials are. So this differential is x. So stuck to it should be the things containing x. So not this. So this has to move. So what we can do is divide both sides by y cubed. And so that would end up looking like this. Okay, and you can put it either under the whole thing or just under the dy, or anyway, I'll just put it under the whole thing, I guess. Okay, and now we're still not done because stuck to this differential dy, certainly we can't have this expression containing x. So I would now divide both sides by that radical, and that is going to look like this. Okay, just like that. And now we're certainly in much better shape because we do have the variables separated correctly. Now, I did that in 2 steps. It's also possible to go directly from this step to this step by dividing by y cubed and the radical all in the same step. Okay, now we cannot integrate this with y cubed in the denominator. The only time you leave the variable in the denominator is when the exponent is 1, right? Because that's when it'll be logarithmic form like this. But here it's imperative that we make this y to the negative 3 dy in order to integrate it properly. And on the right side, the square root sign here corresponds to a fractional exponent of 1/2. But then again, we wouldn't leave that in the denominator. So what we have here is actually a fractional exponent of negative 1/2, like this. And now the left-hand side can be integrated just using that most basic integral rule again. So all we have to do is add 1 to the exponent, so it'll be negative 2, which means that right in front will be 1 over negative 2. Okay, so that's integrated fairly easily. But for this integral on the right, we're going to need a substitution of u. So I'm going to do that down here at the bottom of the page, okay? So again, we're going to go through this in hope that you will start to remember all of these processes, okay? So this is the integral of x times 1 plus 4x squared to the negative half. So what we would do in this situation is call the binomial inside the bracket u. So u is 1 plus 4x squared. What will du be? Well, du is the derivative of this. And its derivative is 8x dx. Okay, so how does this compare? This is x dx. It is not 8x dx. So over here, what we have is 1/8 of du. So this integral becomes 1/8 of the integral of u to the negative half du. Okay, so that's how you use a u substitution. It's the inside of the bracket that you call u. The derivative of 1 plus 4x squared is 0 plus 8x to the 1. So it's 8x dx. And since we didn't have 8x dx, but rather just x dx, we have 1/8 of du. And this is the u to the negative half part. And now all you do is integrate u to the negative half using that basic rule. So what do? We take negative half and add 1 to it. So that gives us a positive half, and in front of it would be 1/1/2. And of course, that is multiplied by the 1/8 that was there already. And then we would also have a plus c here. Okay, so what does this become? This is the same as 1/8 times 2, so a quarter. So we end up with 1/4 u to the half plus c. 1/4 u to the half plus c, or 1/4 1 plus 4x squared to the half plus c. And that's what goes up here then. Okay, so that's looking pretty good actually, except I can see that I'd like to clear out these fractions, and so I'll just change this temporarily to a C1. So in order to clear out these fractions of 1/-2 and of 4, I'm just going to multiply. Now I could multiply them by 4 or by -4. I think I'll choose -4, so I'm going to multiply this term by -4, this term by -4, and also this term by -4. And so that'll look like this. Okay, so this becomes 4C1. Oh, actually, no, negative. I just went through the rigmarole of saying it was -4. So that's -4C1, which is pretty good. And then I think the next thing I'll do is just rewrite this with a positive exponent. And here we'll go back to radical form. So 2/y squared, and maybe here, so here we can have our radical back, because exponent of a half corresponds to square root of, And then this is still minus 4c1. And finally, you know, since c1 is arbitrary, we might as well just call this constant c right here. So I'm going to change this to plus c. And I'll bring this to the other side where it can be added. Okay, so in this last step, I just brought this term to the other side just to make it positive. That would leave negative 4c1 here, but I'll just change that to my final constant c. And I can make a little note for you that my c is equal to negative 4 times the original c1 value. All right, and there's that example, number 14 from your books. Okay, I will take a look at the next one with you. Oh, this looks dreadful. No, it's fine, I'm just teasing. Okay, so here we have dy over dx. Okay, so the first thing we're gonna do is move the differential dx. So that means multiplying both sides of the equation by dx. So let's take a look at that. And that's because we never want those differentials to be in the denominator. Okay, so that's looking better already. Now, the problem here though, hopefully you recognize the problem with this is that there is an x squared in it, and stuck to the differential dy cannot be an x. So how can I handle this? Actually, the best way to handle it is to common factor y from this binomial. So that will look like this. If I common factor y from these terms, we'll have x squared plus 1 in here. Quick check, if I were to open up the bracket using multiplication, I would get this back. Okay, so now then, if I want to eliminate x from this left side, I can divide both sides by this binomial right here of x squared plus 1. So dividing both sides by x squared plus 1 will look like this. Okay, and now we have variables separated. So that's good. However, we might not know how to integrate this right side. Okay, so I think that we're going to go to the bottom of the page in order to try to integrate this right here. The left side should be straightforward for us. It's y to the 1 right now. So in order to integrate it, we add 1 to the exponent. There will be 1 over 2 in front. Okay, for this integral, I'm going to go to the bottom of the page. So let's try this together over here. Okay, so believe it or not, this is going to require a u substitution. Now, it's hard to know what to call u here. Should u be x squared plus 1, or should u be tangent inverse of x? If you call u x squared plus 1, you'd be thinking maybe it will be of the form 1 over u, so it'll be logarithmic form. But if u is x squared plus 1, its derivative is 2x. And this numerator is not a multiple of 2x. So that wouldn't work. Let's try calling u tangent inverse of x. If I do that, then du is the derivative of tangent inverse of x. So let's see if we can figure out what that will be. In fact, it's here on our formula page, okay? Or this would be inside the back cover of your textbook. Okay, so you can find this inside the back cover of your book. The derivative of tangent inverse u with respect to x is 1 over 1 plus u squared times du by dx. So we're doing the derivative of tangent inverse x with respect to x. So it's just 1 over 1 plus x squared dx. Okay? And actually, that's exactly what we have here is u multiplied by du. And I can show you that if you open this a little bit, it would be the same as that multiplied by that. Okay, see how it's combined here, but it means the same thing as having this multiplied by this. All right, if you multiply these two things together, you'd get this. Okay, so this is u, in other words, and this is du. So we have the integral of u du exactly here. This is u and this is du. And what's the integral of u du? Well, it's u to the 1. So its integral is 1/2 u squared. And then plus c. Or 1/2 of u is tangent inverse of x. And so that's what's going to go right here, except we're going to temporarily call that constant c1. Okay, so 1/2 tangent inverse of x all squared plus c1. And the reason we do that is because we can see that it would be a good idea to eliminate these fractions by multiplying all terms by 2. So this would then be 2 times c1, or we can call that c. So c here is 2 times the original c1. Okay, and that's problem 20 from your textbook. So a little bit tricky when it came to integrating here. We have to remember that we could write it this way. This is u, and if this is u, this is exactly du. And again, that's using the formula right here. Okay, I think we'll just do one more together in this first video and more examples in a second one. Okay, so this is problem 30 from the very same exercise. We have y prime right here. So y prime is the same as dy by dx. So that's a first thing I'm going to do in this question is change y prime to dy over dx. After that, we never leave the differential in a denominator. So how can we fix that? We can multiply all terms by dx here. Oh, this was not smart of me. Look, the variables are actually y and t, not y and x. So this should be dy by dt for this example. Sorry about that. The independent variable is t in problem 30 and the dependent variable is y. Okay, so this will be dt. All right, so that was the first main step, changing y prime to dy by dt and then multiplying the terms, this term and this term by dt, and that gives us this. Okay, now here's dt. So we cannot have y squared in this term, so we should divide the terms by y squared now. Okay. Looks all right, but now here, the differential is dy, so we cannot have this binomial, which contains t. So now we'll divide the terms by e to the t plus 4. And that gives us this. And we're very close now, except we never leave this in the denominator. So we're going to make this y to the negative 2. Like that. And this left side can stay just as it is. Okay, now this time it's the right side that is simple to integrate. In integrating y to the negative 2, just add 1 to that exponent, like that. Okay, and then here we would have a constant. For this integral right here with respect to t, I might go down here at the bottom of the page. And we're going to use a u substitution. So what I'm going to do is call the denominator u. So the denominator is e to the t plus 4. So that is u. What is the derivative of e to the t plus 4? Well, the derivative of e to the t is just e to the t. And the derivative of 4 is 0. So we get e to the t plus 0. And don't forget dt would be here as well. So this is trying to remember how to differentiate and integrate the exponential function. So the derivative of e to the u is e to the u. The integral of e to the u is e to the u. But having said that, if you have e to the 5x, and I said, what is its derivative? Then that would actually be 5 times e to the 5x. And if you had e to the 5x and I said, what is its integral? That would be 1 over 5 times e to the 5x. Right? So I'll just come back to this paper in a minute, but just a reminder. Okay, if it comes to exponential functions like this, e to the 5x, if I said, what is the derivative of that? It's 5 times e to the 5x, right? If instead I said, what is the integral of e to the 5x with respect to x? It is 1 over 5 e to the 5x plus c. Okay, so this is just a little reminder on how we handle the exponential function, how we form its derivative and its integral. But in this case, it's just e to the t. It's not e to the 5t or anything else. So the derivative of e to the t plus 4 is just e to the t. Okay, so remember, just like I showed you in the other one, this can kind of get broken up. It can get broken up into 1 over e to the t plus 4 times e to the t dt. Just so you can see more clearly then, this is 1 over u times du. See? That's the du, and that's 1 over u. So we end up with the integral of 1 over u du. Or that's the same, of course, as the integral of du over u, if you like that better. These are the same. And what's the integral of that? Well, that's just our ln u. Okay? Plus c, but the constant's already been taken care of for the whole equation. You just need one constant for all integrals in that equation. Okay? But in general, yeah, there'd be a c here. And don't forget, don't leave the u here. We have to put back e to the t plus 4 in its place, just like that. So this is now the left side. The left side is the ln of e to the t plus 4. Okay? And this is... Oh, how did I have my, sorry. The equal sign wasn't here. This was a plus sign back here. Sorry, I kind of mucked that up a bit, right? So just going back to this line right here, all I was supposed to do is take this very equation right here, this very equation, and divide each term by e to the t plus 4. So that means that this was a plus sign, and we still had equals 0. Same thing right here. Oops. Plus sign. And equals 0. And then lastly, right here, this was still a plus sign. And this can now say equals c. Sorry about that. That's a big mistake on my part. The plus sign is still here all the way. The equal sign comes after this dy by y squared term. Okay, and that means also after the integral here. Okay, so somehow I moved the equal sign to here. And anyway, let me just finish this example. So this would be the same as a negative sign, and it's y to the negative 1 or 1 over y, and this can remain c like that. Okay, and I think we'll stop there. So I believe I just went through 1, 2, 3, 4, 5 questions with you. Yes. We did problems 4, 8, 14, 20, and 30. So I'll stop there because the videos tend to get a little bit long otherwise. I'll stop there, but I'm going to do several more examples with you in the next video as well. And whenever you're feeling somewhat ready, you should begin looking at the odd numbered problems on your own from the same exercises. I've posted already the solutions for those questions that are provided by the publisher. So if you get stuck while you're working on them, you might find it helpful to refer to those solutions as well. Okay, thanks a lot for watching. And again, the course, I know at the beginning, it's going to seem rather difficult, but I promise you will get into the swing of things as soon as all of these integration rules start to come back to you. Okay, thanks. Have a good day.